Welcome to the second lecture. So here we are going to talk about a very familiar thing called functions. Everybody has heard about functions. If I have gone through high school, I must have heard about function if I was attentive in the math class. So function is essentially a machine which gets one input, it gives you an output. So just think of a machine like this, a machine which I call a function, and there is an input which I call x, and there is an output which I call y. So here is the input which gives me an output. But remember, there are some restrictions in this machine. This machine cannot give you two outputs with one input. So you take a piece of potato and chop it into two. So you have one potato, this gives you two pieces of potato. So that cannot happen, right? Cell division, you have a cell, biological cell, it divides into two equally identical parts. So such operations are not functions as per mathematics goes. So here if I have one input x and there is some machine which gives me say two outputs corresponding to this x, which is y1 and y2. So this is not a function. So function has the rule one input gives me one output. But of course, one important thing is that a function can have the following behavior. I can have two different inputs which gives me the same output. So this is accepted in a function because x1 is giving me one output which is y1 and x2 is also giving me one output which is y1. So at the same time they are not giving me two outputs. This also has a meaning called set valued maps, which we are not going to even talk about here, though economists would need it. If I have time, then I will really speak about it a bit. For example, now output is usually written as y and the input, that is the function or the machine f, is acting on x. So this machine f acts on the given input x, gives me output y. So in mathematics we call it the independent variable. So I have the choice to give my input, and this gives me output. Output or dependent variable. This is also called a dependent variable. So these are some very basic facts you have to know about functions. For example, if you take the function f(x) equal to x square, we are only talking about real numbers here. So all my inputs here are real numbers. For the time being, all my inputs here are real numbers. But it is not that I cannot have any other thing. I can have anything as an input, any object as an input. But for us, all our examples would come from real numbers. So if I take f(x) equal to x square, it is a familiar parabola that you know, you have studied in coordinate geometry. This is a function, and you see here for x1 equal to 2 and x2 equal to minus 2, the function values both f2 and f minus 2, both of them give me the same number 4. So this is a function of the following type here. This function is a function of this particular type. Now the one which we had just said, the two different inputs give me one output. But for example, the function f(x) is equal to 2x plus 1. So one output gives me one input gives me one output. But it's very fundamental thing to remember that if we twist this function a little, say we look at this function, not a function or this curve, I would say, y square is equal to x. Then is this a function? The answer is no, because y gives me plus minus root over x. So corresponding to a given x, I have two values of y, you see, that is where it cuts the curve. So a function, here you see what I have done, I have tried to draw certain graphs here. So concept that is intimately linked with a function is the notion of a graph. So, when we are talking about functions about real number, we are talking about the graph of a function. So, it consists of two real numbers x and the function value f x, y basically. So, where x is somewhere, I would write some set x, which is a subset of the set R. I am assuming that you know set theory. So, because I have already mentioned that these are slightly a course for the first year level, not for +2 level students. So, graph of a function. So, you can think something like this. This is looks like a graph of some function. Of course, I am unable to write down exactly what function it is. For example, if you say f x equal to x cube, now to be more precise, let me go back to the high school definition of a function, which you already have some idea about. In your high school, they teach you the following definition of a function. They said, let us take two sets which are non-empty, x and y. And by a function, one means, so this is my x, this is my y. And by a function, we mean a rule which takes up one point x in x to only to one point y in y, not to 2 points or more points. So, f takes this x to this y. So, y is often as we have written as y equal to f x. So, I can talk about arbitrary sets. Functions can be defined between two arbitrary sets. It need not be even defined just between two real numbers. So, this is what you learn in your high school. So, this set x is often called the domain, and this set y is called the codomain. There is another concept called range of the function, range of f, or in short RANF. It consists of all elements in the codomain. So, it consists of all y in this set y for which there would exist an x in x such that y is a function of x, y is equal to f x. So, this means that I am trying to say that there need all elements of y need not be an output corresponding to a given x. That is something very, very important. So, there is a difference between codomain and range. So, essentially what we are trying to say, range is the subset of the codomain. So, range of f, also called the image of x under f. Sometimes the people use the terminology as f of capital X. I will give you an example how these two are different. For example, I take again the standard function f x equal to x square. Here the domain means, when I am talking about a domain, means I have to operate this function f on each and every element of the domain. This is of fundamental importance, that each and every element of the domain has to be acted on by f. So, if I take f x equal to x square, I can square any real number. So, domain, which I now write in a short form dom f, is R, but domain of f is, or the codomain of f is, which I write now as codom. The codomain of f is also R, but the range of f is not R, because it only gives me non-negative number. It is the set R plus. R plus is a set of all x such that x is greater than or equal to 0. See, it is set of all x in R, x, all real numbers are. So, x here is in R, and these x's must be greater than or equal to 0. So, it is just one side of the number line which you have an idea about. So, we are just here. So, my range is a subset of the codomain. For example, now I take the function f x equal to logarithm of x, natural log of x, where the base is the number e. Then the domain of f is R plus plus, that is the set of all x belonging to the real line, that is all real numbers which are positive. Of course, you know the log, you cannot define log for a negative number or 0. Now, what is the codomain of f? The codomain of f is R. Codomain of this log function, codomain of log is R. So, what is the range of the log function? The range of the log function is also R. So, codomain now has become equal to the range. When codomain of f becomes equal to the range of f, we say that the function is onto or subjective. We say that f is onto or surjective. If we are speaking about some other sort of behavior of functions, an important behavior is a one-to-one relationship. That is, if you have two functions such that f of x, if you have a function such that f of x1 is equal to f of x2, then it should imply that x1 must be equal to x2. It cannot be that two different numbers has given me the same function, the same function value. It can happen. For example, in fx equal to x square, we saw -2 and +2. So, fx equal to x squared, it does not satisfy this definition. So, this sort of, if something satisfies this definition, it is called injective or into function. So, a function is bijective or one-to-one correspondence. Function is bijective. We have used the word bijective in the last lecture. If function is bijective, if f is both surjective and injective. Now, we come to a very important notion of the inverse of a function, because this question is natural. You might ask, why are you talking about inverse? So, but the question of inverse is a very natural concept, inverse of a function. So, what does it do? It does the following. Inverse means, for example, I take the function y is 2x plus 1. So, here I have expressed y in terms of x. So, what happens if I swap it? Means I make y as the independent variable and x as the dependent variable. Then can I write x as a function of y? So, here y is a function of x. My question is, can I write x as some g of y? In this case, the answer is yes, because I can write the whole thing as x is equal to y minus 1 by 2, which is my g of y, right. So, but it might not always be possible. So, inverse of a function which we denote as f inverse sometimes. So, g is here called f inverse of y. So, f inverse of a y, where y belongs to the domain, right. So, what is f inverse of y? You take any y and then you ask the question, can I find an x in x such that y is equal to f of that x? So, there can be more than one x for which y is equal to f of x. So, if I take the function f x equal to x square and if I take f inverse of 4, then I have this set would consist of 2. So, for example, if I have f x equal to x square and then I ask you what is f inverse of 4, then this set consists of 2 elements +2 and -2. So, f inverse is really not a function, because for a single element here 4, I have 2 outputs +2 and -2. So, one input giving me 2 outputs. So, f inverse need not be a function in general. So, when f inverse is a function, we said that the function is invertible like the one we have just done, and then we can say that the function has an inverse. So, f is invertible when f inverse is a function. When is f inverse a function? A very important result to remember is that a function is invertible if and only if it is bijective. This is absolutely fundamental to one's understanding. Now, what can we do with functions? We will give you some more examples to play on with. So, finding inverse of logarithmic function, and there are certain cases where you can write down the inverse exists because the function is a bijection, but you cannot write it down explicitly. So, we are now going to talk about some more properties of functions called increasing of functions from of real numbers. So, in our study we would be largely considering functions defined from R to R, or functions defined on a closed interval a b or an open interval a b, doesn't mind. So, functions of this form, these are the type of functions we would be interested in our study. So, in our study of calculus, these are the type of things which will come repeatedly. We will talk about limits of these functions, continuity of these functions, integration, differentiation, and all sort of stuffs about which you have heard about. But now it is very important to us to know two important types of functions which play a fundamental role in the study of calculus. These are called increasing functions and decreasing functions. So, what sort of function is called increasing? So, if I take x1, so I take a function from real number to real number, R to R, and the first one, this one, and if I take x1 bigger than x2, whenever this happens, if I have f of x1 strictly bigger than f of x2, I said that the function is increasing. There is also a concept called non-decreasing, which says that if x1 is strictly bigger than x2, the function value at x1 can be strictly bigger than fx2 like this one, or can remain the same. Similarly, you can talk about decreasing functions. For example, in that case, we have whenever x1 is strictly bigger than x2, you have f of x1 strictly less than fx2. In a similar spirit to the non-decreasing function is the notion of a non-increasing function, and we will see that how derivatives has a role in understanding of these type of functions. So, whenever x1 is strictly bigger than x2, it will imply that f of x1 must be less than or equal to f of x2. So, you can immediately in your mind imagine and draw graphs like this, functions like this which is increasing, functions like this which is decreasing. So, if you take fx is equal to logarithm of x, then that function is obviously an increasing function. Or if you take its inverse, fx is equal to e to the power x, that sort of function is an if you come from this side, is an increasing function. So, this is the graph of e to the power x, e to the y equal to e to the power x, and there is a graph of log x, logarithm of x. So, these type of functions are very, very important, and these play a fundamental role in calculus, and that is exactly what we are going to talk about. Another important thing that I want you to note at this stage, at the very end, is that you have to also keep in your mind that when you use the notion of function, never ever by mistake think about inverse functions, like for example sine inverse functions. People use sine inverse functions, sine inverse x. This is standard in calculus, in our trigonometry. Sine inverse x function, is it sine inverse x? We use it as if it is a function, but is it really a function? The answer is no. Because for example, if you draw the graph of sin x, what would happen? So, sin x is a function whose domain is R and whose range, by the way, is -1 +1. All the values vary between -1 and +1. So, for such a function, what is the meaning of sin inverse x? Because you see, at this point the sin value is 0, at this point the sin value is 0, at this point the sin value is 0, at this point the sin value is 0. So, sin inverse 0 occurs at n pi. So, but when you write sin inverse 0, in many cases we just write it to be 0, means we are using one of the values of this set of numbers. So, it has to be very important that when you work with inverse trigonometric functions, never think of them really as functions. Inverse trigonometric functions are not functions, you are just using one of the values of this function, which is in this case 0 is called the principal value. So, this has to be very kept in mind, because trigonometric functions are very important, because Fourier analysis or Fourier series that you learn about has a major role to play in engineering sciences. So, it is very important that you keep in mind that inverse trigonometric functions, which can never be a function, they are always so called set valued maps, which are not functions. But when we write sin inverse x equal to y, we are essentially talking about only one of these values, and a value which is chosen, the first value or the base value, which is called the principal value. So, the inverse trigonometric functions are not functions. So, these are very important example of a thing which is used as a function, which looks like as if it is being used as a function, but it is not really a function. We will talk about sequences in our next talk, in our next lecture, and I hope that you are having a more or less basic idea about what's going on. Thank you very much.